All right, our next section is 7.6, which is called linear programming. So linear programming involves systems of equations, inequalities actually, and solving for feasible solutions in real-world applications, business applications. Um, if a company wants to maximize profit based on some certain constraints that exist within their group, that involves linear programming. An interesting one is FedEx, or any sort of a delivery program involves linear programming, where you want to minimize the amount of time spent on the road in order to maximize delivery efforts. That's linear programming. So they have entire courses on linear programming in college. All right, so let's just start first of all with just a theoretical one, and then we'll go to an application problem next. So first of all, a new term that we have is what's called the optimization function. So this one here, the z in this problem, optimization, is that is the function that we are trying to optimize, either minimize or maximize based on whatever our situation is. Optimization function. And then the constraints are whatever is put upon us by, finance or ability, how many people are working, or, whatever our constraints would be. Again, we'll go to an application in a minute. Let's just focus on how we solve these first. So we actually are going to start by graphing. We do not graph the optimization function. All we graph are the constraints. So let's graph these. I'm going to do these in different colors. Let's start the first one. X is greater than, or actually let me put in my little tick marks here. 1, 2, 3. No, you know what? I'm going to make those just a bit bigger so that we can really see our function well. Functions. All right, so let's start by graphing. I'll do the first one here in blue. X is greater than or equal to 0. So we know that x equals 0 is a vertical line. So we're going to say it would be right here on x equals 0. And if it's greater than, we know that it has to be like this. All right, our next one will be y is greater than or equal to 0. So that's a horizontal line on the x-axis, and we know that this one is going to be greater than, would be here. All right, our next one, it looks like is a linear. X plus 2y is less than or equal to 4. So let's pick another color for that one. Let's go with the purple. This guy will be purple. So if I'm going to use, you can use whatever method you want. I'm going to use the intercept method. So if y is 0, x would be 4. So x, that'll cross right here. And then if x is 0, y will be 2. So it'll be right here. He will be. And we know that this guy has to be less than or equal to. So you can pick a point to figure out where you're going to shade. If I pick the point, I'm going to go with 0, 0. So 0 plus 0 is less than or equal to 4. That is true statement. So I know that my graphing or my shading here would be down here. It's getting to be a little bit of a mess. Okay, and then my next one is x minus y. Let's do green for this guy. X minus y is less than or equal to 1. So using the intercept method, if y was 0, x will be 1. So 0, 1 right here. And then if x is 0, y will be negative 1. So it'll be this one right here. So we're going to graph this. And this one says is less than or equal to 1. So I got to figure out where I'm plotting here. I'm going to plug in 0, 0. So 0 minus 0 is 0. 0 is less than or equal to 1. That is a true statement. So this guy graphs up here, above it. So mine is really a mess. But ideally, you're looking for what area do all four, fits all four of these constraints. Hopefully you can see that it's actually this area right here, the yellow. Actually, maybe I'll just take off some of my shading now that we have, I don't want to take off the line. So it can, yeah, that's a little better looking, isn't it? So we're just gonna, there we go. So now that we've done that, oh, that was not what I wanted. There we go. Let's go back to the yellow. So this area here fits all four constraints, and you can always pick a point. You could say like 1, 1 is in this area. Just make sure your point is very clearly in that fully contained within the constraints. And then you could test them up here if you wanted. You could test 1 is greater than or equal to 0, true. 1 is greater than or equal to, I'm testing the point 1, 1. 1 is greater than or equal to 0, true. 1 plus 2 times 1 is less than or equal to 4. That's 3 is less than 4, true. 1 minus 1 is less than or equal to 1. 0 is less than or equal to 1, true. Okay, so that's clearly our section. All right, so after you graph them, you've graphed your constraints. So now what we're trying to do is remember we were trying to solve this optimization function up top there, the z equals. So now what we do is we're going to take our the intersection or the vertices of the region that has been shaded. So the vertices of our region is, this one here is 0, 0. It may help to write down your intercepts as you're graphing them so that you don't have to go back and figure out what they are. Mine was pretty clear. This one is 1, 0. But, you know, if you had something like a third, you should probably write it down as you go. This intersection here, we actually don't have that. So we might have to solve that one algebraically. So that's where the purple and the green functions meet. So that was x plus 2y is less than or equal to 4. Take off these stray marks here. And the green one was x minus y is less than or equal to 1. If I were solving this system, remember we just treat these like equals signs when we're solving. We learned from our last section. If I multiply this guy by negative and add them together, I'm going to get 3y is equal to, 3, not 4. 3y is equal to 3, and that means that y is 1. So plugging in, it doesn't matter which one I plug into, just plug into one of them. If I plug in the top one, x plus 2 times 1 equals 4. That means that x would be 2. And this one looks very close to 2, 1. But don't guess where these intersect, because mine really looks like it's a little higher than the y value being 1. So you do not want to guess. You want to definitely solve these algebraically. So this intersection point is 2, 1. I'm going to erase all this because we don't need it. All right. And then the other vertice of our shaded region was this, oh goodness, sorry, all right, was this guy up here, and that one was 0, 2. I found that from graphing the line. All right, so these are our 4 points. So the way we solve our optimization function is we take these 4 points, we plug them into the optimization function, and then we see which one, if we're trying to maximize it, we look which one gives us the max value. And we are trying to maximize this one. If it said to minimize it, we would look for the min value. So let's try them. It is z, let me write it down here, z equals 3x plus 2y. So I'm going to plug each one of these in. So I'll try 0, 0 first. Z equals, 3 times 0 plus 2 times 0. This one gives me 0. It's pretty obvious this will not maximize this function. So the next one, z equals, let's try the 1, 0. 3 times 1 plus 2 times 0. This gives me 3. All right. The next point, z equals, let's try the 2, 1. So 3 times 2 plus 2, 1. Again, I'm getting these points from these vertices up here. These are the ones I'm testing. All right, so this one gives me 6 plus 2, so that'll give me 8, this point over here. And then my last one would be 0, 2. 3 times 0 plus 2 times 2. This one gives me 4. So obviously, if I'm maximizing this function, this one right here gives me the max value for my optimization function. So that means that the solution here, which the question was, find the max value of z equals 3x plus 2y, given these constraints, then the max value would be 2, 1. All right, let's look at an optimization profit problem in this case. Pause the video and read the problem here. I don't want to read it for you. So I'm going to jump straight into how to solve this guy. All right, so first we have to identify our optimization, our objective function. Our objective function is what we are trying to optimize. Objective function. So we want to optimize our profit, right? That is what is the maximum monthly profit. So our profit comes from, so we'll call P our profit. Our profit comes from the number of chocolate covered creams we sell, plus the number of the profit from those. So it's $1.50 per box. So let's define our variables real quick. Let's say X is going to be the chocolate creams. All right, let's say Y will be our chocolate nuts. So our profit comes from, it says above that we get $1.50 per profit per box of creams. So $1.50 times X will give us our profit for the chocolate covered creams we sell. And we should say the number of chocolate creams sold. This is the number of sold for both of these. And then we're also going to profit from our chocolate covered nuts. So that's $2 per box. So $2 times Y. So this is going to be our objective function that we are trying to maximize our profit. All right, but we do have constraints. So we have 3 of them listed above. So let's see if we can define our constraint functions. Constraints. All right, so the first one says the combined production level should not exceed 1,200. So that means that our X plus our Y, because these are the number of boxes, our X plus our Y must be less than or equal to 1,200. Should not exceed. Maybe we don't have the equipment or the materials to produce more than 1,200 boxes. All right. Then our next one says the demand for chocolate covered nuts is no more than half the demand for the chocolate covered creams. So the demand for the chocolate nuts, which is Y, is no more than. So that means it is less than, it could be equal to, is no more than less than or equal to half the demand, half the chocolate covered creams. Okay, and then our last one, the production level for chocolate covered creams should be less than or equal to 600 boxes plus 3 times the production levels for nuts. So that means that our chocolate covered creams should be less than or equal to 600 plus 3 times the chocolate covered nuts. So we literally are just interpreting the terms into mathematical operations. All right, so here's our constraints, and here is our objective function. Okay, I went ahead and graphed this. So here's what these 3 functions will look like. The blue, I gave the colors like I do always. The first one is the blue, that's the blue line. The second one is the purple, and the third is the reddish color. Okay, so if you remember from the last problem we did, first we need to find all of these. Please note that I did not even go in the negatives because the negatives don't matter. We're not going to produce negative amounts of boxes of nuts or creams. That doesn't make any sense. So logically speaking, we stay in that first quadrant here. All right, so now I need to figure out where all of my vertices. We said the first one is 0, 0. In all honesty, we don't really even need to check that one because clearly producing 0 boxes of nuts and 0 boxes of cream is not going to maximize our profit. So my other vertex is this one right here. So that is an x value of 600, y value of 0. My other one is here, my other one is here. Now remember I told you in the last problem, do not guess at these. You need to find these analytically, find them. So I need to find where the blue and the purple meet. So if in this case, blue was x plus y, I'm going to put equal to 1200. And the purple is y equals 1/2 of x. We can do this multiple ways. I think I'll do substitution. I'll just plug in this one into that one. So I have x is equal to, I have x plus 1/2 of x is equal to 1200. Which gives me, this is 3/2 x equals 1200. Multiply both sides by 2/3. Okay, and then solving for x, we're going to multiply both sides by 2/3. So x should give me, multiplying by 2/3, we are dividing by 3. So that should be 400 times 2 would be 800. All right, so that is my x value. Remember my y value comes from that. So y is equal to 1/2 of my x value, so 400. All right, so that vertex right there is, the x value is going to be 800 and the y value will be 400. So that one looks pretty obvious, but again, it's not smart to guess. I'm going to erase this. So then we're going to find the vertex for the last set, which is my red and blue. So the red and blue. Blue is x plus y is less than or equal to 1200. That was blue. Red is x is less than or equal to 600 plus 3y. I don't know why I put the inequalities. I told you go ahead and put the equals in there. Let's just put them as equals. I guess I'll do substitution since it's set up for substitution. So I'll plug this guy into this one. So that'll give me 600 plus 3y plus y equals 1200. So this gives me 4y is equal to 600, which means that y is equal to, what's that, 150? All right, so my intersection there will be the, we didn't find the x value, sorry. X value, so we've got x plus 150 equals 1200. So x would be 1050. All right, so that next one is 1050 and 150. That's an example of one that I would not have known by guessing. I would have no clue that x value just by looking at my graph. All right, so these are my 4 vertices. So if you remember, the next step is to plug them in to my objective function. So my objective function is the profit based on each, the number of sales. So, oops, we don't want that. All right, so our objective function was p is equal to 1.5x. I just dropped the extra zeros. We don't need those. All right, plugging each one in. I'm just going to plug straight in and give the solutions. So 0, 0 obviously is going to give me 0. No good. So my next one is 600 and 0 are my 2 points. When I plug those in, 1.5 times 600 plus 2 times 0, this will give me 900 profit. My next profit, let's try the 800 and the 400. So plugging those in, 1.5 times 800 plus 2 times 400 This one gives me 2,000. And then my last one, so I've got 1050 and 150. So my profit here is 1.5 times 1050 plus 2 times 150. This gives me 1875. So that means to maximize my profit, my optimization function, my objective function, to maximize it, it looks like this guy here is going to be the max profit based on those constraints. So my solution here will be 800 chocolate, those are the nuts, I think. Yeah, no, those are the creams. 800 creams and 400 chocolate nuts will maximize my profit. And then I think the question asked us for how many boxes of each type and what is the maximum profit. So the profit is the 2,000 and then the boxes are 8.